We're now going to learn about a new concept in this course known as entropy. And so before we get into the details about entropy, I just want to give a brief introduction. As we saw in your MEB courses, the concepts of the conservation of mass and energy are foundational principles that guide engineering. In particular, we saw that the first law of thermodynamics was a very useful tool for analyzing or modeling energy transfer in both closed and open systems. So, first law of thermodynamics is a powerful tool for modeling energy transfer. Okay? And so as you saw in your MEB2 course, you could use the first law of thermodynamics to study a wide variety of different processes, both those that involve reactions and those that don't involve reactions, and processes that are at steady state or at unsteady state, a wide spectrum. All right? But by itself, the first law of thermodynamics isn't enough to fully understand a chemical process. So by itself, however, it is not sufficient. Okay? And that's because with the first law of thermodynamics, it could tell us how energy is converted from one form to another, but it doesn't tell us anything about direction or if there are any restrictions in how that energy can be converted. Right. So first law by itself might imply that energy can be freely converted from one form to another with no restrictions. Right. Energy from one form into any other at any time without restrictions. Okay. But as we know from observations and just experiencing real life, that's not true. To paint this clearer, we could think of one form of energy transfer, heat. From the first law by itself, it may seem to suggest that heat can transfer in any direction. It could go from things that are hot to things that are cold, or vice versa. Heat may be able to flow from things that are cold to things that are hot. But what we know in real life is that heat really only flows in one direction. Heat only flows from things that have a high temperature to things that have a low temperature. Okay? And we never see the opposite happen. Right? So that's one thing that, the first law of thermodynamics doesn't really accurately capture. Another thing that we see in real life is that if we're trying to convert energy into work, whether it's heat or whether it's some sort of reaction, the energy from that initial form, not all of it gets turned into work. Right? So in real life, not all of energy put into system, if you will, or extracted from the system, is converted into useful work. Okay? And in fact, what we normally see is that some of that energy is lost through kind of what we call irreversible mechanisms, which are kind of like side kind of like side reactions. If you think about chemical reactions, but these are kind of like side energy transfer mechanisms. You know, other things that happen that consume energy. All right, and so these irreversible mechanisms, the energy that's lost in the system, we could kind of think of it as a form of lost work. And this concept of lost work in a process is what we refer to as entropy. Okay? And so in chapter 4, what we're going to do is, in addition to the first law of thermodynamics, we're now going to learn about the second law of thermodynamics. Which deals with the concept of entropy and how it can not only be conserved, but it could also be generated as well. So we're going to learn how to quantify entropy, and then based on this quantity of entropy, this will be able to help us understand if a process can be performed efficiently or if it's performed inefficiently, or if it's a process that can just not actually physically occur. So if it's physically impossible, such as the case of heat flowing from low temperature to high temperature. Okay? And so to at least motivate why we should learn about entropy, I want to go through a kind of quick example and profile a famous engineer named Otis Boykin. Okay? All right, and so here's a picture of Otis Boykin in the top left here. He was born in the early 1900s, and he graduated and earned his degree from Fisk University in 1941. After college, he worked in various research laboratories as an engineer, but he didn't become famous until about the early 1960s, when he invented a new type of resistor. And so, as you may remember from your Physics 2 class, a resistor is a device that controls current, or in other words, it controls the flow rate of electrical work. All right, and so typically resistors, back in the old days, before the 1960s, they were just made of a coil that was wrapped around an insulator, like this. Okay? Could probably draw a better one. So imagine something like this. Okay? Where the coil, it was either made up of like carbon, metal, or some sort of metal oxide. Right? And so for this resistor, you put a current in, it passes through the coil, and then it comes out the other side. All right? And we could also describe a resistor using our traditional black box approach, where you could kind of think of a resistor as something that accepts some sort of work electric in, and then it also puts out a electric work as well. Okay, so that's the whole concept of a resistor. But as we saw, when normally with resistors, what we saw is that not all of the electric work that goes in was able to come out. And the reason for that is that some of the energy from that electric work that was put into the resistor was lost. Okay? It was lost either as heat, or some of that energy was lost due to inductance. Because, if you remember from your Physics 2 class, if you have some sort of coil and you apply an electrical current through it, that could create a flux of inductance through that coil, right? And so that process consumes energy, right? And so back in the old days when they were making resistors in this format, a lot of the energy that was put into the resistor was lost due to inductance. And so, to sort of, minimize this issue, what Otis Boykin did is he developed a new type of resistor in which all he did was just coil the resistor coil in an alternating pattern, where one section was like this, and then another section was coiled in the opposite direction. And so because of that, the inductance that's formed from one section of the coil then gets canceled out by the inductance in another section of the coil. All right? And so by coiling the resistor in this format, you actually eliminate that W lost from the resistor process. Okay? All right, and so just by making this kind of tiny improvement to a resistor, this enabled resistors to be made on much, much smaller scales. And in fact, being able to design resistors that were very, very tiny then also led to improvements in other devices, such as the pacemaker for helping people who had irregular heartbeats. Previously, because resistors had to be really big, pacemakers also had to be really big and plugged into the wall. But because of Otis Boykin's invention, they were then able to make pacemakers that were much smaller and could be operated just simply through using the electrical work that comes from the human body. Okay? And so based on Otis Boykin's invention, he saved countless lives throughout the world. And that's because all he did was just minimize the amount of lost work that was lost through the resistor process. Okay? And so in this chapter, we're going to focus on how we could understand and minimize lost work in chemical processes.